to start to make the connection between the formation of the molecular ion, the fragmentation patterns, and the corresponding mass spectrum. We start with the simplest of molecules, methane, and the representation here at the top is the formation of the molecular ion. You can see that the methane is bombarded by a high energy electron. One electron is knocked out, which results in forming the molecular ion. So often, as mentioned, the molecular ion is represented simply by brackets around an M and positive charge, but this is representing an actual structure. This is referred to as a radical cation. Clearly it's a cation. It's radical because there are an odd number of electrons. Now often we will show this by putting the structure in brackets, put a positive charge outside the brackets, and we'll also put a single dot outside the brackets. In this case, we're showing the single dot as being a single electron holding together two atoms. In this case, we know that it must be one of those bonds that has the single dot, so we reflect that right in the structure here. Now, if we calculate the nominal mass, so this is rounding off the atomic masses to the nearest integer and adding up those numbers. So for instance, the formula for methane is CH4, and so of course carbon's nominal mass is 12, and we have 4 times 1 mass unit for hydrogen, so that would be plus 4. So the nominal mass for methane would be 16 atomic mass units. If one electron is knocked out, the nominal mass is still 16 atomic mass units. And so we see over here a peak in the mass spectrum corresponding to 16. So of course this peak would correspond to the molecular ion with a nominal mass of 16. Remember again, the x-axis in a mass spectrum is m over z, but z we assume to equal 1. So essentially this is reflecting the molecular mass in atomic mass units. As it turns out, with this very simple molecule, the molecular ion peak is also the base peak, because as you can see, this is the peak that is in the greatest abundance. The way that the mass spectrum is measured and output is that the highest peak, the most abundant peak, is arbitrarily set at 100%, and everything else is compared relative to it. Notice that this is unusual in that the molecular ion peak is not normally the base peak. There is some fragmentation that occurs though. So there's a substantial amount of molecular ion present, but then in some cases the molecular ion has fragmented into smaller bits. A common fragmentation is the loss of a single hydrogen. Now one of the ways that we'll show this transformation is to use curved arrows. A little bit later in the course we'll highlight a lot the use of curved arrows. So I'm showing here a lone pair of electrons, and if I take a curved arrow and I draw a double-headed arrow, well, that's showing the electron flow for that pair of electrons. However, if I start with a single dot, which represents a single electron, and I draw a curved arrow, I would use a single-headed tip of the arrow to represent that that's a movement of a single electron. So in terms of the fragmentation that happens here, the single electron ends up associated with the hydrogen. This, of course, results in a full carbocation, the positive charge associated with the carbon, and that's the fragment that's detected. This fragment here is lost, and we know it's lost, but it's not actually detected. And of course, this fragment would give rise to the m over z of 15 that shows up here. You can see that there are some other fragments, and of course the only possibility is that in going from 15 down to 14, a single hydrogen is lost, and 14 down to 13, another hydrogen, and 13 down to 12, another single hydrogen. We can represent this, though, in a fragmentation diagram. So what I'm going to do here, I'm going to start here first of all with my methyl cation. This is not a radical. That is, it does not have an odd number of electrons. And as you know, the m over z for this is 15. Let us see how this would be transformed to go to something that has m over z equal to 14. Now the idea is that it fragments further, and we're going to lose a single hydrogen, and it'll leave behind a cation that would be detected. This again would involve the movement of single electrons. And effectively, one of these bonds will get broken. I'm going to pick on the bottom bond, and I'm going to use a single-headed arrow to show that one of the electrons goes to the carbon, and the other electron would go to a hydrogen. And so we will lose this single hydrogen atom as a radical. What will be left behind is also a radical cation with two hydrogens, positive charge, and I'm going to draw a single electron to show indeed this is a radical. The nominal mass for this would be 14. Of course, this process can be repeated again. As you notice in the spectrum, fewer and fewer particles actually exist as these fragmentations continue. And so again, what would happen is a single-headed arrow to that hydrogen, a single-headed arrow to the carbon. We're left with carbon-hydrogen, positive charge. Now 2 electrons like that. So technically speaking, we now have an even number of electrons, so that's not a radical. So this guy here is a radical, whereas what we've just formed in the next step is not a radical. However, it's still a cation and would be detected. And then lastly, we'll lose another hydrogen, atomic hydrogen. This would be lost in the following way: 1 electron to the carbon and 1 electron to that hydrogen, and then we would have dot, 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 positive charge. So over here, m over z equal to 13, and over here, m over z equal to 12. So we're drawing out the fragmentation pattern to explain those peaks. But this is not to say that any of these things are particularly stable. It's just explaining how the process might have occurred. We will do more examples later in the activity, so you get more practice with this. The next thing is to consider, well, what sort of information can we glean from analyzing the molecular ion peak? And one of the things that we can glean is the actual molecular mass of our compound. Now, the molecular mass can be thought of as either in terms of high resolution or low resolution. Low resolution reports the molecular mass essentially in nominal units, that is, comparing the molecular mass of 58 to 60. Whereas high resolution allows us to look at the mass to a high level of precision, to several digits past the decimal place. Low resolution is still informative in terms of distinguishing between compounds that have a substantial difference in nominal mass. So for instance, these two compounds here, the C3H6O and C3HO, could be distinguished by low resolution mass spectrometry. And as it turns out, in this course and in our analysis in the chem activity, we'll mainly work with low resolution. However, if you have a high resolution instrument, you could actually distinguish the difference between these two compounds, which effectively have the exact same nominal mass and only differ when you look very precisely at their masses to several significant figures. So the distinction between these molecules with identical nominal masses could be done with high resolution mass spectrometry.